Hi. In my last video, we looked at bond polarity, and that'll play into this discussion of intermolecular forces, or they're also known as IMFs. Intermolecular forces, as we're going to talk about today, fall under the umbrella of something referred to as van der Waals forces. Van der Waals forces are interactions between particles that are not charged. So not between ions, but there's still some sort of interaction. We break these down broadly into three categories. It's really only like two types because one is a subset of the other, but we'll get into that. So one, we have something that's called either London forces or dispersion forces, sometimes called London dispersion forces. Okay, so we have London forces. I also see them called dispersion forces, or sometimes London dispersion forces. Number two, we have dipole. Oh, let's back that up. Dipole interactions. And this is generally between molecules that have dipoles. Doesn't have to be, but it often is. Sometimes called the dipole-dipole interaction. And there's a special case of dipole where it's exceptionally strong compared to other dipolar molecules. And this is hydrogen bonding, also called H bonding. All right. To speak of the first one, so we have London forces, or I'd prefer to call them just dispersion forces. These are interactions between molecules that are not polar. So these are between nonpolar molecules. Or particles. Okay. I'm going to scroll this up here. It depends on like how shiftable the electron cloud is of a given particle. So the way we interpret this is if there is a larger electron cloud, if there's more surface area to the molecule, therefore more surface area to the electron cloud, it's more shiftable, and therefore these dispersion forces are greater. So the way to think about that is if you have a molecule, let's say we'll pick something, I don't know, like oxygen or something, I don't know, like O2. Not the greatest example, but you have maybe these centers of positive charge in the nuclei, and we have, oh, don't know what happened there. We have our electron cloud here, where we have the negative charge. Now, there can be a temporary shift in this electron cloud to one side. And if we have a temporary shift, what that means is that, albeit temporarily, there is now a slight negative charge up here and a slight positive charge down here. As you can see up here, there's more of the electron cloud up in this area, and so this side of the molecule is temporarily more negative. And down here, there is less of that electron cloud, and so it is temporarily more positive. This is due to dispersion of that electron cloud, and that's why it's called dispersion forces. It's short-lived, it's temporary, and it's not very strong. It's a pretty weak interaction But what happens is you get some of these molecules with these temporary shifts next to each other, and they kind of hold together a little bit. If you have a longer molecule, and I'm not going to draw the whole thing, but like if you have a hydrocarbon, 1, 2, 3, 4, 5, 6, 7, 8. You have, I'm not going to draw the hydrogens, you'd surround that with hydrogen. You've got now this electron cloud around this whole thing. Okay, there's more surface area to it. And let's just, for contrast here, let's say we look at propane. You got 3 carbons, and here's its electron cloud around here. Again, there's hydrogens all around that. I'm not drawing them. What you'd perhaps get out of this is that this electron cloud is larger and it's more shiftable because there's more surface area to it. And so because it's more shiftable, because there's more there to shift, you're going to end up with, after it shifts, a larger area of partial positive and a larger area of partial negative than it would be possible down here with propane. So we can see this relates to some of the characteristics of these different molecules. We know that propane is definitely a gas at room temperature, and that octane, or gasoline here, is a liquid, although it has a high vapor pressure, but it's a liquid at room temperature. And the reason why it's a liquid is because there are greater dispersion forces between the molecules than, say, for propane. So this is propane, and this is octane, or the main ingredient in gasoline. Those are dispersion forces. So we only find this, just as a reminder, here between nonpolar molecules. If you look at what the different bonds are in these molecules that we've talked about here, we could look and see that, like, the CC bond is not a polar bond. The CH bond is, as discussed in the previous video, not a polar bond. If we don't have any polar covalent bonds, that molecule is going to be nonpolar, and it will rely on dispersion forces for its interactions.